Sounds good.
While Alan's doing that, if anyone's not familiar, I'll post Alan's channel. It's Space Audits. I'll post this as the stream currently, so if anyone wants to see where it's being streamed there.
All right, hello and welcome everyone to Celestial Theodolite update number 27. Tonight's an exciting night. I believe after this Prezi ends, there will be a presentation by the Globe Coalition. They'll be doing a presentation on the Celestial Theodolite, to which we will do we'll post their video on our YouTube channel with a timestamps for any comments or things that need refuted or whatever. So good luck to them on their Prezi tonight. And we'll cover some of that next week. But shout out to those lads for taking a look at the data and whatnot. Now, before we begin tonight, we're going to take a new approach to Celestial Theodolite in terms of looking at it in terms of mini eclipses, because we're going to have a bunch of time to go over rather than dealing with all these angles and what does this unit mean, what does this mean. Like, we'll go over that obviously, but the important part to take away, and like a way that you could argue it, is just off of timing. So we'll touch on that. But before we get into that, we're going to recap on the null hypothesis, the very backbone in which this all started. So what is the null hypothesis anyway? The null hypothesis is when you take two mutually exclusive outcomes. In this example, we have our H naught being that the Earth is round. So this is the thing we're going to assume is true. And then we have our H1, which is our null hypothesis, which is the Earth is not a globe. So two mutually exclusive things here. One's flat, one's round. They both can't be the same thing. So we have two different possibilities here. And now we are going to examine some timing differences to facilitate how to determine which one of these is likely correct. So in the hypothesis versus null hypothesis method, you have what you have here, what you assume to be true as your hypothesis, and your null is the mutually exclusive opposite, and then you try to falsify that. If you falsify that, then your hypothesis is likely true. If you fail to falsify your null hypothesis, then the original hypothesis is likely not true. So very simple, straightforward logic. If one of these is true, the other is likely not true. Or if you can't prove that the other one is false, then the other one is likely false. So for the Celestial Theodolite setup, we have it broke down into an IV, DV, and control. So for the IV here, we have the observer distance to the peak and relative elevation above sea level. So that's going to be our benchmark for the IV, and you can manipulate that by going a different distance to the same peak. The control is going to be the known elevation of the mountain peak, no matter how much you change your distance or elevation relative to that known mountain elevation. The mountain elevation is going to be the same. So we use that as our control. And then to determine, where's our DV there? Yeah, our DV is going to be the occlusion angle. So that's going to be dependent on the manipulation of the IV with respect to the control. So how close or far away we get to a peak is going to dictate the angle of the occlusion time. And then the occlusion time itself happens naturally as the star occludes into the mountain peak, and then we take the time and get our angles and do our analysis after that. So we've got our three variables there.
Are you supposed to be sharing?
Yeah. Yes, I am. Yep. Thank you, sir. My bad. Here we go. Back it up a little bit here. I'll give everyone a second here to file in. My bad. I missed anything fancy yet. It's just text right now. So just a quick recap: hypothesis up top in the H naught. The H1 is going to be our null. If you falsify one, the other one is likely true. If you fail to falsify it, then the other one is likely not true. And then I gave the control IV and DV here for our setup. And as we go down here, so this is just some more on null hypothesis testing. So there's two versions of hypothesis testing. There's the naive falsification and sophisticated falsification. Naive falsification would be falsifying a hypothesis with no statistical analysis. So, like for example, if you took black swan and said, there's no such thing as a black swan, but then you see the black swan, well, that would be a naive falsification because it would just be one instance of it. To have a statistical analysis of it, to have the sophisticated falsification variant, you would have to have at least 3 black swans. That way, you can't say it was like a genetic mutation or a one-off or something like that. So it just adds like a level of statistical confidence to it. And that permeates through not only physics and science, but also in the world of finance and stuff. So I found a couple of accounting websites that do a null hypothesis method for how they determine profitability or viability in investments and whatnot. So there's all kinds of ways that you could apply this as long as you know your variables and what you're doing. You can do either a sophisticated rejection or a naive one. So either one is either one of those is valid depending on your whatever you're using it for. All right, so with that said, here we have 2 different timings that'll be possible for eclipses. Now, let me 1 second. Let me bring up my Canva here so we can see. It's templates. I need projects. All right, projects. Astro refraction. Okay. So the way the stars and angles are tied together, especially for the globe believers, we have a unique opportunity here to test 2 different occlusion timings for stars. So the beauty of this is the way that, following the same way that eclipses are predicted. So if you go to this NASA link here, you'll see it's the Fred Espenek page, and it has all the data tables for all the eclipses that they go through to predict. But you'll see here that they're all done in geocentric coordinates. Now, this isn't to be confused with geocentrism of old, of like Tycho Brahe and Kepler and all that. The geocentric coordinates in this context is referring to the true position of the moon and the sun, meaning the unrefracted true position at zenith when somebody measured it on the equinox, and then adding 15 degrees per hour to those. So those are the true positions that are used for the intersection to occur for an eclipse to happen. So that is what they use. So in the same respect, we're using the raw geometric features of what flat Earth would be, just using plain trig of rise over run to the mountain by taking our difference in elevation times the known. No, it would be our difference in elevation times the known distance, and that would give us an angle for rise over run. So we have 215 here. So we can track when the star is going to be at 215 with respect to the observer and also with respect to the peak. And we can compare and see when these, what happened during these occlusions. So what they do to predict this is using the true positions. And again, we're following the same suit here. So when this star for the observer, the way that this diagram, let me move over to this diagram so it's a little easier to see. You can get rid of this for now. Okay. So for this diagram, we have Nicki Minaj here. She's going to be our observer. We have our line of sight. That's a little curve there. That's for the lads. And we have it just grazing the tip of this peak here. So when the true position of the star relative to the observer, going from left to right here, so the text on the left here is all positions with respect to the observer. On the right, at the same time, is positions of the star with respect to the peak. So what we can do here is if we take this section of sky, which is 27 arc minutes, and that's 27 arc minutes of difference between this number right here and this number right here. That comes out to 27. And based on how fast the stars vertically drop in the sky, we know how long it's going to take to traverse that 27 arc seconds. So if we were to get in Stellarium and rewind this by 2 minutes and 29 seconds, the angle would be about right here, say, and then 2 minutes, 29 seconds would pass by, and we would have this potential intersection here. So when the true position of the star for the observer intersects with the peak right here, the same angle, this 217 angle for the star is the same as the geometric peak elevation predicted for the globe, accounting for 200 meters of drop. So if the 200 meters of drop is true because you're on a sphere and it's tilted away from you, then that physical elevation level is going to intersect with a star at 1842.04. And you can get in Stellarium and verify all of these angles, and we might do that at the if we have enough time to, when I wrap up here. So anyway, this intersection was completely missed, and 2 minutes 30 seconds goes by. Now the star is at 206 for the observer, and it's at 233 with respect to the peak, and this is where it finally gets occluded. So what do we do with this information now? Now we have our actual occlusion time. The orange is noted as the actual occlusion time. So we have our actual occlusion time, and then a few seconds later, I think it's like 10 seconds or something like that, 11 seconds later, we have our predicted time for flat Earth. So we're super, super close there on that. Now, what do we do with that information, though? Okay, well, we take our predicted elevation angle and we subtract it from the true position of the star at the peak. And that gives us a difference of 2 arc minutes. And that also converts into 11 seconds. So we were 11 seconds off the measure of our prediction. So in 11 more seconds, that's what it would have had, the perfect geometric alignment. Now, we're not even going to get into what could cause the offsets or anything like that right now. Right now, we're just looking at the raw time for now. Okay. Now, for the globe, down here highlighted in the darker pink, is where we do the exact same thing. We derive elevations and distances based off of occlusion timing. So to show the formula here, we have distance times the tangent of the occlusion angle. And this is just where the star was at the time with respect to the peak for us, for flat Earth. And then for the globe, we take the intersection angle of their predicted geometric elevation for the mountain there. And we take the occlusion angle for them, which would be the true position at the time of occlusion for the observer. So at the time of occlusion for the observer, the star is at 206. So we take their predicted amount of intersection difference minus where the star was for them, for the observer, and we get 11 arc minutes of difference. So in other words, the globe missed their prediction by 1 minute and 3 seconds. We missed our prediction by 11 seconds. Now, a lot of the globe lads would say, well, what about refraction? Isn't there refraction? Isn't that a thing? Well, not only is it a thing, but it's a particular type of thing, especially when it comes to astronomy. So I found a couple of examples here, and I've been through this before on some of my previous prezzies. If you recall back to the one we did on astronomical refraction explicitly, I talked about how the refraction amount has to be invoked as a 1-to-1 ratio for how much it's lifting the star. So in other words, if they say that the star is 15 arc minutes below the horizon and it has negative coordinates, but it's also 15 arc minutes positive for the apparent position above the horizon, then that means there's 30 arc minutes of refraction between the two to compensate for the drop below the horizon and then to lift it up above. So that's how you get the total amount there. And then once the apparent position goes into the negative coordinates, that's when it would be considered actually occluded by geometric Earth curve. Now, obviously, when you get into optics, someone's hot micing me. 1 second. Gotta fix that. Whoever that was. All right, sounds good now. Okay, so when talking about that refracted position, all of that refracted amount has to be used up before it's considered occluded. Now, obviously, before it gets that far to the horizon, we can't see that far. There's an opaque layer that's like about half a degree up or whatever from the horizon. So you're not going to make it all the way down to see it like that. But that's theoretically what it would be, and that's how it's mapped out into Stellarium. You could confirm that yourself. But check this out. There was an observation in what was it? In like the 1500s. Yeah, 1596. Captain Wilhelm Barnetz was leading a polar expedition on the 76th latitude. And at that time, the sun was supposed to be 2 weeks below the horizon still. It was at the time, it was supposed to be negative 4.9 degrees below the horizon. And they observed the sun at 4.9 degrees above the horizon. And then in the first case that this happened, Captain Wilhelm was like, "No, there's no way you saw that, my dude. That's complete BS." And then so 3 days later, he made the same observation and confirmed what his sight guy saw, and was like, "Okay, my bad for stepping." So anyway, they call this the Novaya Zemlya effect. And what we see here from the diagram is that the sun is 4.9 degrees below the horizon, but it's also 4.9 degrees above. And they have some explanations for someone's hot mic. And can you get that for me when you get a chance? Um, what you can see here is the sun's below the horizon. They invoke a temperature inversion that's over unity, actually, which is pretty crazy. And then after that, there's a gradient that's, man, someone please grab that. It's James Brown. All right, I got it. I got it, guys. Okay, so see this darker area here that they have? This is supposed to be some duct layer that has a perfect refraction gradient, essentially, of like inversion, where it's greater than, or close to unity, and then under unity. So it just creates this bouncing layer effect that just kind of carries the image of the sun up and down all the way to the observer over here. And what that means is any amount of refraction that's needed to explain any observation is the amount that will be invoked to explain the observation. So there will not be, like, they didn't measure this amount of gradient or anything. Nobody went out and measured this. This is all calculated based off of what it would have to be to facilitate the conditions for this. And then this, of course, was later observed in 1914 by Shackleton, who was doing an Antarctic expedition, and the sun was supposed to be 2.7 degrees below the horizon, I think it was, and they ended up seeing it above the horizon by 2.7 degrees, and they just chalked it up to Novaya Zemlya effect. So when we get into the accounting for astronomical refraction here, what I found through my studies is that below 15 degrees in the horizon, it's pretty much a no man's land. No astronomer really wants to touch it. They've got calculative models that predict, or not predict, that curve fit to what is observed, and that's what they call astronomical refraction. It's computed from from the troposphere layer. They say that it doesn't interact with the boundary layer that we observe. Like, if you were standing on the ground looking out at the horizon, they would say everything below your eye level is dictated by this lower boundary level of like thermal radiation and ducting and stuff that happens due to the density of air at that layer and whatnot. And then as you get a few kilometers higher than that, there's it tapers off, and then it's not connected to the tropospheric stuff that they calculate. So they keep them separate. But in this case, where we're 15 degrees, or where we're like 2 degrees off the horizon, etc., it's really just calculated effects for how much astronomical refraction there is that stellarium is reporting for, and all that's doing is maintaining the 15 degree per hour relationship by giving lift over distance, essentially. So it's essentially explaining why the star is still visible when it should have been occluded by Earth curvature. And let's see here. So if I give these values for refraction as they're as told to us by stellarium, then if there's no occlusion here, these numbers stand as the number that's needed to fulfill the Novaya Zemlya effect. You can think of it as, because this is the number that it has to be. Because if it's a different number, then it's not following the 15 degrees per hour, etc. So I am willing to give the astronomical refraction, but you must use it in its entirety in the analysis of the geometric intersection of what you would consider to be the peak at 217 here. So if you guys are ever over your geometric peak at the time of occlusion, you are thus not occluded. So when we look at that from the analysis, we have the raw geometric intersection like we have for flat Earth. We have the same for the globe for their raw geometric intersection. And we even have the bonus refracted amount to see if that intersects with the peak or not. Because the thing about refraction and occlusions is when you have a refracted image, no light rays converge there. It's an apparent image where there's no light rays converging. So other light rays intersecting with it are not going to be occluded by it. We're only interested in the geometric intersection, but we'll throw in the astronomical for funsies. If you were to occlude based off of the refracted position, you would also be breaking the law of reversibility. And that's an optical thing where basically the object that you're looking at, you would have to be able to trace it back to its original ray source. And if you cut it short like that, you're not going to be able to do that. So the refracted position doesn't help any more than just it's not a factor I'm willing to entertain in terms of like an actual explanation, but I will show you the numerical value of how off it is, or how much over it is over the peak anyway, and how much longer it would take for that light to go and reach the peak. No, absolutely correct, Bull Knight. A reflected object does not do that. I actually have a demo of that right here. We'll take a quick look at it. I have a quick example of that. It takes 1 minute. If you're tuned in, I'll show you real quick. Here we go. All right, a quick lesson on the principles of the Cel-Theo. So what we're looking at here is, you can see the pattern of that light is distinctly different from the lights that are in this hallway here that are being reflected out into the mirrors or windows there. But what you'll notice here is that the reflected beam, so like this right here, gets reflected out into the images, and as we move over, we can see that when we intersect the reflected image, it doesn't block the light. The direct light source is right there, doesn't get affected when we move into the reflected images, right? The only thing that actually blocks that light is the physical object, and we must overcome that to see the light again. Okay, so what we're looking at here as we move, you see now it's in the reflected image, no occlusion. Same concept as the Cel-Theo. Nice. All right, so are there any questions about the analysis in terms of comparing flat Earth to what flat Earth predicts and comparing globe Earth to what globe Earth predicts? Semi-transparent seems non-analogous. A semi-transparent window provides a plane for the image to be projected into, and the projected image is all that's required for the, that's what's being, that's the analogy, right? So if in a homogeneous medium, the image is being lifted up with non-convergent light rays, then it's the exact same. Like we did, that's what the point of the cup of water and the laser pointer was. Same situation, but people don't like that one for some reason. So. All right. So keep in mind here, the flat Earth side is done with plane trig. The globe Earth side is done with the spherical law of cosines using spherical trig. And more about spherical trig can be found here. And let's see, where did I add that? Is it here? No, that's not it. 1 second. Where did I add that? Oh, notes, trig notes. Here we go. So there's a book from Smart on spherical astronomy, and this guy, Ars Frank, he has a book on plane and spherical trig. So central angle theorem and all of that is covered in here. And then how to use central angle theorem and all that is covered in Smart's book. So all of these formulas and everything that we're doing is all, up to snuff in terms of representing the globe accurately. We're doing it all through spherical trig and no plane trig. And then again, showing the convergence of the light rays, you would have to be able to trace it all the way back for the law of reversibility. If you end up cutting it short to match our time, well, then you're breaking this line, and that's illegal. I'm not a cop or anything, but it is illegal. All right. So again, we take our time of occlusion, and we take the difference from what we predicted, the angular separation between the two, and we just subtract it. And we get 2 arc minutes. We get a 30-second offset. We're off by, I'm sorry, this is meters. We're off by 30 meters, because we can also convert this angle into distance, because Distance is also convertible into angle, or angle equals distance, using central angle theorem and all that, which is what the globe is all predicated on. So we can turn this into a meter amount. So we see that this is 30 meters of intersection difference. Now the globe, of course, had 169 meters of intersection difference. It's a weird number. It's about 170. If you take these two and add them together, it's 200. It equals what the drop over distance should have been. So in this comparison, how much we're off versus how much the globe is off. Oh, I'm sorry. I'm comparing the geometric intersection. So this is how much the globe was off from their geometric intersection. When you go to derive elevations off of what the globe predicted for their occlusion angle by how much they're off, they missed their mark by Earth curvature, and we share that same error. So if we take the 169 that they're off that they derived for their elevation, and we add it to the 30 that we were off, we get Earth curve. So the difference in the half central angle also basically tells us which model was more correct. Because if the globe had occluded at the time that it was predicted for the globe intersection, we would be off by 11 arc minutes, and we would share this error. The globe would be off by 30. It would have like a 2 arc minute separation or whatever, and then these would be reversed essentially. The difference in how much we're off would be reversed, but the amount of curvature, it would still be within the confines of that half central angle, because that is the expected geometric difference between our two models. So it's really interesting that based off of the timing of all this, because it's all related to time, we can see exactly how much Earth curve was not present in the measurement. And this continues through all the measurements. We can analyze it through that method. Any questions so far? All right, I take that as a... Oh, go ahead.
I was just wondering, what was that one ducting diagram you showed with the bouncing rays? That guy who saw the sun up above the horizon when he shouldn't have, or whatever.
Yes,
First off, that was hilarious. That diagram is, the way the light is bending is absurd there in that diagram.
Dude,
it's actually
no straight lines for you on a globe unless you're making a diagram to explain why the sun was seen 10 degrees above where it shouldn't have been.
Yeah, it's crazy. Did that have a name?
Yes.
What is the name of that?
Novaya Zemlya.
All right, I'm gonna write that down. That's interesting.
Yep. Oh yeah, I'll give you here's the link to the paper.
Can I ask why you're using that? What's the point of using that refraction index?
The point of it was to show that when refraction is invoked as an explanation, the full amount of refraction is the amount that you have to use to make your argument. You can't use like a custom amount and change it. What the amount is given is the full amount 1-to-1. So what I mean by that 1-to-1 is that they say that the sun is 9.4 degrees below the horizon, but it was observed 9.4 degree, or I'm sorry, 4.9, I set that backwards, but it was observed 4.9 degrees above the horizon. So they need 10 degrees of refraction here to lift this up, and they never measured that or anything like that. They just calculated out what it would have to be via these kinds of diagrams where they say that along the way, there's a thermal duct that creates these conditions where the light rays can bounce up and down essentially like this. So the purpose of that was to solidify the amount of refraction prescribed at the horizon when stars set into the horizon, and it's said that they're being occluded by the Earth curve. You can go into Stellarium and see, when they're given negative coordinates to be below the horizon, but they're still visible above the horizon, there's a refraction amount, and until that full amount of refraction is used, the star is still considered to be above the horizon for the apparent position. So even though it's below it, it's still theoretically should still be visible.
So how many of your demonstrations or your observations, are in the Arctic or Antarctic regions?
None of them.
Oh, well, that's what that effect is for the Arctic and Antarctic regions. So why are you using that?
As I just explained, it's to show how the amount of refraction needed is the amount that will be invoked to explain the observation anywhere on Earth.
Well, no, that effect. Well, I'll just leave it at this. But that effect, if you read in those paragraphs that you showed, were only for the Arctic, where you're in polar regions, not in general the wherever the U.S. or wherever you're doing the observations. It's only in the polar regions.
I don't disagree, but it shows that, like I said, the full amount of refraction invoked is 1 to 1 for the lift. So it must be fully compensated for in order for there to be an occlusion. So in the examples of stars getting occluded by peaks, when there's still refraction left over for the star to be above the peak, it is thus not occluded, as per all of the other instances where the globe would claim that refraction is lifting it above whatever 1 to 1. Okay.
It's also just
So let's
highlighting
see.
how these claims are just being made about refraction without actually, being able to actually test them. They're like theoretical refraction.
Well, this does give a good chance to actually test it because occlusions, are based on the physical the physical intersection between source and physical object. So if refraction worked in the way that they said it did, flat Earth would be off by, 12 arc seconds so that this full transit of that refraction amount could occur. But like that doesn't like none of this ever happens. It's always way shorter than what's shown. And to take it back to the example with Goose, although the example is kind of poor, we show that the actual angular separation between the object doing the occluding and the refractive medium on the other side, you have to physically, like the object has to physically be behind that object. And if there's and if there's a refractive medium between the object, I'm sorry, between the light source and the object doing the occluding, that the light source will have to move a little further behind it before it gets occluded for the observer looking at the object doing the occluding. So and that was quantified by the difference in angle there. It's kind of hard to see, but small angle here when there's no medium, and then after putting the medium in and then taking it out and measuring the difference in occlusions there, it had to be moved further behind the peg there before it would actually got occluded. So like we don't disagree that like refraction's a real thing and it has effects and whatnot, but it's not necessary for us to even consider it for what we're doing for our predictions because the effect of how much we're off is pretty minimal in most cases where we're not at sea level. Now the most extreme cases that we've seen are when you go to when the observer is at sea level and you're at a low angle like that. Um, let's see a couple of the measurements from old Blinn. There was 20 arc minutes of refraction for that one, and then there was another one at Blinn at a further distance where it was 25. So we can see here that the amount of refraction, they definitely have an amount to say, hey, this is why this is at this angle when it's supposed to be, here with respect to 15 degrees per hour or what have you. But it isn't this full amount because in the measurements for how much we were off, the intersection difference was only was only 10 of that 25. And if you think about it like this is kind of crazy. Like I've mentioned this a couple times, but I think the significance of it was kind of lost. But this is the full angular drop in the sky. So how much the star is moving in the sky relative to the observer. And if there's a refraction, so this 22 amount here, 22 arc minutes. Now, if there's 25 arc minutes of refraction, that's completely compensating for all the drop to the star. That's essentially like 2xing Earth's radius for that star. That's pretty interesting in terms of how the refraction works. And then, like even when you go to a case where it's not as extreme, what you'll see here. So like if we go to above sea level, like Blue Mountain, for example, and we go to see they have 20. There's 26 minutes of drop here. And then there's 18 minutes of refraction, which is a lot better than having it fully compensate for it. But you'll notice that the half gamma, which is which would be the Earth curvature along this distance here, is pretty much always compensated for by the refractive amount. And then you could see what that looks like in terms of lift. So if their drop over distance is 194 meters for this 49 kilometer measurement, then the astronomical lift would be 273 meters of lift. So it's an interesting way to compare it since we have a fixed distance to put this all to. We can see how it affects that measurement directly in terms of the arc length of that distance and the half gamma, the Earth curve drop over that distance. So, real quick about the analysis. Is there any questions about how we derive everything for flat Earth using the occlusion with respect to the peak, and how for the globe, who wants to be observer centric for everything, we go with where the true position is with respect to the observer's location at the time of occlusion? Like, even if you don't agree with it per se, for some reason, if we're taking the intersection difference from flat Earth, we should do the same for globe too. Like, that makes sense. It's not a trick. It's fair. It's how we know how much we're off. And then if the derived elevation difference still shows that same relationship, then that's a really unique way to compare it to the differences per the Earth curvature over that distance. So if any of the globe lads would like to make mini eclipse predictions, they would need to have timings that facilitate their geometric intersection, because the only geometric intersections that seem to be occurring at any time that's close to what's predicted is for flat Earth. Like, I'm trying to reduce it back to the lowest possible form that we could start with, and just using time. If we see a peak out in the distance, what time do you think it'll be occluded at? Well, there's two different possibilities. If we live on a globe, then the stars are going to follow the Earth curve as they traverse the arc length that they're, between us and the thing that's going to occlude. And because there's curvature on that arc length, we know how much elevation is missing from the top of that mountain. Therefore, we know its angle. If we know its angle, we know what time that star will also be at that angle for us. If there's a geometric intersection, we've got ourselves an eclipse, boys. Oops, where's my eclipse? Got ourselves an eclipse. So try to think of this in terms of mini eclipse predictions. If angle equals time, then we could make mutually exclusive predictions on when the star will no longer be visible. It's going to get blocked by a mountain peak. Is it going to be blocked by a mountain peak when it's predicted by the globe? It's going to be right here. Nope, it actually turns out to be right here. What's the time difference between these two? How much did we miss our mark and how much did we miss their mark by? Well, you can determine that right here in the spreadsheet. There's our intersection offset. There's their intersection offset. Here's our elevation that we derived using plane trig and the occlusion angle. Here's their elevation that we derived using cosines and the radius of Earth. And we get, that's weird. We're off by 170 meters. That looks familiar. No, that's their intersection difference. Wait a minute. Their intersection difference plus our intersection difference error turns out to be globe curve. Huh. that's strange. And then why is there more air on the globe side? Shouldn't it be on our side because it got occluded by a mountain peak due to globe geometry? It's pretty much that straightforward. Everything else in terms of the angles and the math is all supplementary stuff that you don't necessarily need to argue, but it's all here. Every bit of it. Since we started this project, all the corrections to how the globe should predict and derive things were changed by flat earthers. We were told you were using the wrong equation. Da, 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 da. Well, we found all the right equations to use now. No one gave us one. No one's actually corrected anything that's made this time go back to the time that was actually measured. None of the things that have been changed in the spreadsheet actually change the globe time to make it so that it's fits what the globe predicts. These are massive geometric failures for the globe. This intersection difference that happened here is because the Earth isn't a globe. Shane, do you have anything you wanted to add?
No, I hear a lot of quiet silence. I guess I'm gonna take that for light acquiescence. I do love the visual demonstration though. So that's just like a warping effect. You're just tilting that in Canva to show the precession of the stars to give it time to show the difference. That's brilliant,
Yep.
dude. Look at that.
Yeah, thanks.
All the
Thanks,
effort we
Brian.
went through to try and depict it, and all you had to do was that. Well, shit. There you go.
It's pretty
That
nice.
explains the geometric difference between all three. It's what we've been trying to show the whole time. And there's no astro refracting or terrestrial refracting out of that, as you clearly show.
Yep. Now let's see here. Before we close out, then I guess because this would be a quick one. Then I suppose if there's no questions, I'm not gonna browbeat everyone here or whatever. But this is the layout. This is how it's always been. There's been some stuff added and changed to better represent the globe. Like when I updated the how to derive distances, it did actually improve the globe. It made it look less ridiculous in some of the measurements. So for North Peak, for example, in this one we're off by 30,000 because this is 130,000 or 130 kilometer measurement. So we're off by 30 kilometers on our derived occlusion angle there, and the globe was off by 170,000, where they were previously off by like 300,000, I think it was. But that was because I was doing arctan rise over run to get the difference, with their occlusion, which made it look a lot worse. They're only off by 170,000 meters, which doesn't help them at all, but it does accurately represent the distance now. So stuff like that is really all that's changed in the spreadsheet.
That's cool because I always thought that one was wrong, and then I couldn't figure it out. So that's helpful. Nice. It always looked fun.
It's still not great, but
no. But it just when you have a tiny error like that, the longer the distance accentuates it, and that one definitely should have been a sign. Because it was a huge 300,000 was huge.
All right, lads. There also has been a rumor going around that there's a hidden radius on this spreadsheet somewhere. So hopefully we'll find out where that hidden radius is tonight. But as of right now, and always pretty much, the driving radius value is right here in B11, I want to say. Where's B11? No, not B11.
20.
B20. So this radius value, you'll see in the formulas here throughout the spreadsheet, I have them all coded, and instead of referencing cells, it references like the nickname for it. So anytime you see E radius, it's referencing B20 right here, this fixed value. There's no hidden radius or any weird stuff like that. So it'll be interesting to see what comes out of the presentation for the lads after we wrap up. Wish them all the best. And like I said, we will upload their Prezi on my channel, and I'll timestamp all their responses to everything. And that's it. But as of right now, this is a mutually exclusive method that gives, that yields flat Earth measurements. It's only agreeing with flat Earth. Even when we go to the instances where a simulator was used to try and measure the globe specifically, we get into this instance where trigonometrically we derive the same elevation as what they predict for their elevation for drop over distance. So we're capped out right here pretty close. But the actual occlusion intersection, we're 12 arc seconds off, which translates to 1 minute 25 seconds of being off. The globe missed their intersection by 18 arc minutes. They're 2 minutes off. So even still, where this was set up, it doesn't contradict our results, and it actually shows that. And their difference here, they're off by 3 times the Earth curve, which is also what is it? 4 times their refractive amount. So the drop over distance for this is 5 arc minutes, which comes out to be 38 meters. So there should be a 38-meter error here, but there's a there's a 20. That's so crazy. 18
So we've
arc
concluded
minutes.
the globe Earth only exists within the math, and this is what we're showing to prove it. Right? That was Dr. Heffron's immediate and primary conclusion. Oh no, the globe exists only in math, and he devised a method to prove it. And now finally, we're all on board, and we see what he meant.
Yeah. Now check this out. If the globe had hit their intersection, right, we could rewind time to hit their intersection and see what their derived elevations and distances would look like if they were if they hit it dead on. Now, obviously, if they're off by a little bit like we are, there's going to be some difference, but it would be the same kind of difference that is like a natural occurrence rather than like the systematic failure of their exact Earth curvature amount. So this is what they're keep an eye on elevation and distance here. So the distance is 22,000, the target distance, and the elevation is 607. So here they derive an elevation of 486 and a distance of 27,000 meters. Now, if they hit their intersection, they'd be dead on, or at least a lot closer. Like, they would be like 82 off like we are, rather than all of it. So in regards to this intersection difference, this is the difference between our two models, and the globe always shares more of the air. It's like their exact intersection difference is how much they're off on their peak elevation. And in this case, it came out to be 3 times as much as Earth curvature. Or is that? It's almost 4 times. 4 times the amount of Earth curvature. So, and again, if you were doing hypothesis, null hypothesis, in a location where the elevation derived is identical, that doesn't falsify the null hypothesis. If it's non-mutually exclusive, then you have to use a different thing to falsify the null hypothesis. That's the beauty of framing this in the null hypothesis, right? The idea here is to falsify the null hypothesis. Attacking the methodology does nothing, especially when all the measurements comport with our methodology. So their predicted emergence time for this was 156.51, and it emerged at 156.11. So this is an emergence too, so the subtraction thing is backwards or whatever. So they still predict a sooner emergence, but it's less soon than what we would predict. Or it's more soon than what we would predict. And the differences are shown here. So it's actually in this relationship between Earth curvature and how much we're off as the total amount. Like obviously Mike didn't design it that way, like ahead of time, knowing that it would work out that way. But the fact that it works out that way because it's tied to the central angle, it's an incredible marker for to have a way to decide which measurement was closest, because they would literally be reversed if the Earth was a globe. I'd be
that's a good way to.
Dude, I'd be sitting here mopping up all the flat earthers with this, because this would be like the most definitive thing you could do.
The only time we use globe tools is to arbitrarily pick a crap. What did you just say before that?
What's that?
What did you just say before the thing?
Good luck.
Fuck, dude. Your last thing ruined. All right. It was like we only use globe tools when you're trying to, what I would say is, have an independent corroboration or external reference and that
No,
so we're trying
okay,
to. Well, the only time
I
we would
got you.
use that, is that's an objective determination for which one is correct, and that's how we use
Yes.
globe tools. So you can't simultaneously object to using globe tools and still purport the globe, because while using globe tools proves globe wrong. That's the whole point of including astral refraction and including all that, etc.
Yeah, the rhetoric of Haversine globe tool, Stellarium globe tool, using a meter as a globe tool. It's like all these things are ratios of one another that create an internally consistent system that's based off of empirical observation. You're not going to falsify it by just doing observation alone. We need this. We need a secondary thing to introduce, like the control variable of the mountain elevation, and then the relative angle that would produce based off of distance to test this conceptual model that's internally consistent based off of observation. So, like, we
Yeah.
concede that the meter is a ratio of a terrestrial meridian, but when you know what that is, right, that's just a ratio of a circle. None of that has any actual meaning. Like the way that the Chinese had the Li, the Chinese invented the celestial sphere. They used the exact same system, mapped out the north and the south, and using their method of eclipses and star transits, you can accurately determine your longitude sub 1 degree in modern times. So the unit of measurement as a Li or as a meter doesn't matter. The fact that the meter was redefined as a wavelength of light at a certain temperature doesn't matter because it's still tied to its distance that it travels over 1 second, which is tied to inches, which is tied to the meter again. So like it never actually changed anything. Like there are still ratios of one another, all reliant on one another. So using the globe tools to computate distances or angles to stars isn't mutually exclusive. It's just within a self-referential coordinate system that's spherical. So it's going to work best when you use the spherical inputs for it. One of those being a
Yeah.
radius to calculate the distance to make the arc lengths relative to. How else would you convert angle into distance? Well, of course it has to use a Haversine.
Well,
It'd be like trying to use a calculator within like taking the computer chip out of it.
the other way we use globe tools like Stellarium is to confirm our globular predictions because, not to say this is intentional, but all of our globular friends would object with different, quote, straw men until the point that they were all disagreeing with each other. So we had no way to choose, okay, if Ruhiv disagrees with Jesse, disagrees with, and then whose globe prediction is correct. Now we don't need to do that. We just know that our math is coinciding with Stellarium, which is that internal reference check, right? So we're testing it internally, and then we're comparing it to the external variables with changing independent variables. So I mean, I think it's the only time we use globe tools is to check the globe predictions and to choose an objective winner between the two models. So it can be objectionable to either side.
I have a question, if that's all right.
Absolutely.
No, I'm a globalist, so don't take offence if you feel like I'm coming at you. But
I'm taking offended. I can hear the globe in your voice. I'm just kidding.
I can get pretty rowdy, so excuse me if I do. So do you have a maths? Like you're obviously fairly decent at maths. Do you have a formula that you can use that would take the place of the Haversine formula, say for GPS? And that'd be pretty
Not
good.
that, not
And
that,
flat, if you took.
yeah, not that
Go
I'm
on.
aware of. Sorry, yeah, not that I'm aware of.
That that'd be a pretty good thing to have, would it not?
Well, it might be, but my position is that we have a radius of vision, so mapping things to the sky based off of said radius value, I don't see it as like a geometric problem to use the calculator based off of the radius of vision versus a radius of Earth. This is the occlusions that we come up with, is the definitive test to see which conceptual model is correct. Because the use of the Haversine requires two conceptual models to be true. One is the celestial sphere, and the other is the terrestrial sphere. So these two models have to be overlaid on top of one another for them to be true. And if they are true, then that means that the positions of the stars would follow ground curve as they transit over a distance, because that's what's creating the physical elevation change for the star relative to the observer. And all of that is testable by the occlusion timings, because the lads in the 1700s went through extensive measures to make angles equal time. So we can, test on occlusion times to get angles and see which model predicts the correct intersection.
Okay, but does that can it take the place of the Havasine formula?
There's no need to
Which is
replace it.
Proving it's
It's a,
flat
it's a,
would be
it's a, it's a
pretty handy.
fantastic. Well, I already did, because we use the Haversine to calculate what the conceptual two-sphere model predicts for an intersection, and we used the same thing to predict what a flat Earth would predict, or would make for their prediction for an occlusion. And the times that we get occlusions at are only matching flat Earth. So there's no need to replace the Haversine formula, as it's just computating based off of our radius of vision. The drop in the sky is what's being compensated for, not physical elevation drop due to ball curve.
But what about something like GPS?
What about GPS?
Well, it's taking the chord of two positions and applying the Havasine formula to it based on the radius of the Earth. All the GPSs would be wrong. If they're using the Havasine formula and it's flat, they'd all be out. They'd all be wrong.
Incorrect.
But that was what I was thinking of when I asked.
So a better way to understand it would be that if there's curve in the sky, then that's all that's being compensated for, versus curvature on the ground. So there's still curvature, it's just in the sky. It doesn't have anything to do with the shape of the Earth. So the radius value that's being used in that coordinate system has to do with the elevation change at the positions of stars. So it's asserted that based on the 60 nautical miles per degree, that linear relationship is due to ball curve. And then, through central angle and relating distance to angles and whatnot, it actually becomes, half of the arc length is the curvature of that arc length when you get into the full gamma versus the half gamma. So if the half gamma, which is the Earth curve, doesn't exist, doesn't matter. It's still computing distances based off of the full central angle, which is which would be using that radius value to convert a distance into an angle. So it's not going to produce anything that's going to be like erroneous, because it's all based off of positions of the stars as its first reference anyway.
Okay, but let's give it to you that you've debunked the mainstream globe model with this. But in that case, that still doesn't give you the right to call the alternative model that you created a flat Earth prediction if it still has a global formula baked in. The only thing that it would mean is that you have some kind of weird model that's a combination of both a flat Earth and a globe Earth. You cannot say that this is...
Well, let me stop you right
prediction.
there, eMBO. Show me where the globe is baked into arctan or and tangent of distance and angles. That's just plain trig.
In the distance,
so your contention is in the distance that we already said we don't care about, and it comes from a computational model using two conceptual spheres, and we're testing which one of these spheres is correct based off of occlusion angle.
Yeah.
It doesn't. Like,
and don't forget the difference is like 13 centimeters.
One second. And over the distances, right? The difference in distance between the two for our arc length and a chord here comes out to be nothing, but there's still appreciable curvature over these distances, which is what facilitates the drop over distance and the time. And all of this is verified by angles and time. So, additionally, though, I have a follow-up question for you. Do you have any idea where the variant radius is on my spreadsheet?
No, I have no idea. We'd have to ask Jesse. It's Jesse who made that claim. I'm not really familiar with that at all.
Gotcha. I just wanted to be sure, because it seems like there's a big globe secret here that I'm not aware of. I've been trying to ask the Globers about it. Everyone's been hush-hush.
I mean, I've heard about this, but I don't really know where he got that from. So I don't think I'm enough familiar with this to defend this claim, right?
Nice.
I
Didn't
don't
want to
want to
stand next
speak
to that.
for justice from anything.
Yeah, I wouldn't want to stand next to that either. God bless. All right.
Sorry, can I just finish off one last thing, and I'll promise I won't harp on about it. Just one last thing. As far as I'm aware, GPS doesn't use stars and stuff to calculate anything. With the Haversine formula, it plots it says where the 2 points are on the surface of the Earth, and it says how far apart you are in a straight line. So the chord length, and then your phone uses the Haversine formula to calculate how far away those 2 points are. So
The
the GPS only.
position the sorry to cut you off. The position of the space vehicle is marked by, or it's corrected for when it passes D GPS stations, and its latitude and longitude is like always precisely known to have the, where its fixed point is, where it started its calculation from. So it's always inherently in there. Doesn't. And again, I don't contest that GPS is wrong or gives incorrect outputs or anything like that. I got several GPS prezzies, but the main point of this is to show star occlusions, because GPS could be working by some other mechanism. The stars, however, right, only work on two proposed mechanisms. One is that they're following Earth curve, and we see parallel lines coming in, straight down, and then they deviate because of ball curve, or the celestial bodies are moving over top of us and we see in a curve. There's two possibilities here to test with this. With GPS, we'd have to get into other things that we can't confirm or verify. The beauty of this, the celestial theodolite, is that everybody can look up, where the stars are going to be in Stellarium. They can also film a mountain, and then from that they can do trig to the mountain, or we could do it. But the point is that this is repeatable. Everybody could do this, and there are two outcomes that come out of this. And if the Earth were actually a globe, these stars would intersect with the mountain at a different time because of the fact that the Earth is a globe, but they don't.
Fair enough. Yep.
Uh,
We might have some form of D2 was taking a bit off the subject, so appreciate your work. At least you're doing something not like most.
I wanted to clarify something about the Haversine formula. It isn't a matter about there being a curvature in the sky or being a curvature on the ground. The Haversine formula assumes both. It assumes that you have two spheres, that you have the ground, you have the sky, which is also modeled as a sphere, and you have a linear relationship between both, right? Every time in any direction you travel, then the sky will linearly turn 1 degree per 60 nautical miles. And if you delete one of them or both of them, so let's say you assume that the ground is a plane, then you don't have that relationship anymore, because you still have curving sky, but now you have a flat ground. So that relationship wouldn't be projected linearly anymore, because previously it was linear. Now you project one into a plane without projecting the other one into a plane. And now it isn't linear anymore. So when you use the Haversine formula, you're already assuming the truth that both the sky can be mapped as a sphere, and that the ground is also a sphere.
No. So we're not using it to apply linear transformation. We're using it in the coordinate system with which it was intended, the spherical grid of lat long. It's not the Earth or the sky, it's lat long, which is an abstract coordinate system itself. That's what fronts Haversine. Haversine takes input lat long 1 and 2, right? Takes the radius, outputs the distance between those two, as has been covered so far. We're not saying, you're saying that's the Earth. It's not. It's the abstract coordinate system lat long. That's where the distance is computed. We're just saying that we can use that too.
Okay, but when you have the lat long coordinate system, then it assumes a specific shape of the ground. For Haversine formula to work, it assumes that you have two poles, which would be 90 degrees and minus 90 degrees latitude, and basically that the shape of the ground is a sphere. Because, I mean, you can project this coordinate system into different surfaces. That's what maps do. They project it into different planes. Then Haversine wouldn't work anymore.
No.
Here's a diagram of what it actually assumes. We have lat long coordinates for observer 1 where the radius subtends the arc here, and we have coordinates 2 for where the radius subtends the arc here as well. This is the full arc length. This is the radius value. This is turning an arc into a distance. That's all it's doing based off of the radius. It's not assuming anything about poles or anything. It's a literal fucking circle, and then sections of a circle are what are being converted into a distance as a function of the radius.
That was a crazy thing to suppose you just said, eMBO. But yeah, what they actually do is wrap around the actual ellipsoid model. So they compute, like, say, WGS84. They have the abstract lat long. They have it intersect with geodetic lat long. And that's where you get the deflection of the vertical, where the geodetic doesn't match in the astronomic. And they have all the 3 types of latitude, longitude as they interlace those 3 models, as Alan says all the time. So that's where the distance is computed in that abstract coordinate system. And that's how we can use it. That's exactly how it's shown on Alan's screen is what we're talking about. There's no spherical actual surface curving required unless you can verify the ellipsoid model through, surface arc meridian measurements and or astrogeodesy of today.
Okay, so you showed that it isn't a sphere, that it's. You showed that it isn't the sphere, that it's a circle. How does that help you? In what way is a segment
circles have radiuses and spheres have radiuses? It helps us in the way that it's just a computation out of a conceptual model. It doesn't actually represent the shape of the ground, as noted by the difference in eclipse timings for stars hitting mountain peaks. And I think someone yelled out fancy words. You mean an eloquent explanation to how the globe and Haversine works?
Okay, so this for trying to get around the fact that it would be wrong if it was a flat Earth. The Haversine formula wouldn't give us correct distances.
Holy Christ.
Okay, it gives us distances based off of this circle right here. What's different about this circle versus a sphere? There's nothing in here from calculating the arc length from where these 2 points subtend the arc. There's nothing about this that says that this has to be a sphere. It's just a radius. Does a circle have a radius? Does a sphere have a radius? If the answer is yes to both, then you don't have any mutual exclusive things to tack onto it about poles.
Okay, but this is a great circle. A great circle is supposed to be the biggest circle you can draw on the surface of a sphere. Curvature of the circle here isn't on the horizontal direction, a vertical curvature, because it assumes that the surface is curved. If you believe that this gives you distances between places, and you think that's a circle that horizontally lays on the ground, then it wouldn't be the shortest distance anymore, because you would be traveling in an arc. It would be giving you arcs of distance, not straight lines. But it gives you straight lines.
So if your hypothesis were correct, then you would also have occlusion times to match, and I would be here arguing on behalf of the globe, and you could rest easy at night.
Hey, eMBO, can you quantify the difference between the arc length and the straight length, the chord length at 50 kilometers on a 39, or actually, you know what it is, on an Earth radius? You know, what's the difference between those 2 values? Do you know what it is? Did you quantify it before you brought this up?
Yeah. You asked me a question. I'm going to respond. It will depend on your projection that you use.
No, it wouldn't.
It's 14 centimeters.
You're saying it's a globe, and then there's an arc length between 50 kilometers, 2 points apart on the globe, and there's a chord length between 2 points, 50 kilometers apart on the globe. What's the difference between the arc length and the chord length? And Alan just answered that question for you, and it tells you how irrelevant your question is. Completely irrelevant.
Yeah.
So the issue here is that the difference wouldn't only be in the fact that you're straightening the arc length into the chord length. That wouldn't be the only difference. Another difference would be that if you project it into a plane, it would also distort horizontally. So if you look at what are the straight lines on the globe, which are the great circle routes, and you project it into, let's say, the A projection, then they wouldn't be straight lines anymore. They would be curves on that flat surface. Like, let's say the Sydney to Santiago route is approximately...
Once again, eMBO, quantify it. We're talking about a 50-kilometer distance on something that's 40,000 kilometers around. Come on, buddy. Check the ratio.
Yeah, it would be... I cannot calculate it in a matter of a minute.
It's
you have-
insignificant and not worthy of computation.
It's all good, but when you get around to calculating it, let us know how much different it is from 14 centimeters. But on that point, though, if the Earth were an actual globe, we could use the rate of which the stars drop into the horizon and when they'll intersect with physical elevations of mountain peaks based on either drop over distance or no drop over distance. It's like no actual contention or mention of how to rectify that situation. They want to try and be like, oh, you can't even calculate a distance because distance equals globe. Like that's how backwards the conversation has to be taken to avoid this. Complete geometric failure occurred here at 1842.04. The globe failed its intersection. You know, maybe give it a couple seconds. Is it going to happen? Nope. Ended up being another minute and 10 seconds or so before it intersected with the peak at 2:33 with respect to the peak, rather than the observer. So no mention of that. We want to talk about the distance, how we computed the distance between here and here using a calculator for that uses two conceptual models. Okay.
Well, I was listening to the presentation, to the part about the occlusion, and the only thing you debunked was a planet that's the same size as the Earth but has no atmosphere, because you made an excuse by ignoring refraction.
No, we don't ignore refraction. And in fact, I did a presentation months ago about astronomical refraction, going over the intersection differences and how I thought that this was due to actual refraction and optical effects. But we got so far sidetracked off of that due to interjections from certain people that went nowhere. And now we're back on the actual main point of it here, which is you guys have an intersection difference that isn't being met. And even when we compensate for refraction, I can't pull over any further. I can't account for refraction any harder than I've done here by adding it into the spreadsheet, showing how much it's still over the peak at the time of occlusion and how much it doesn't help you by 7 actual seconds. I've quantified everything I show and talk about in this spreadsheet in terms of angle and time and distance. You say, hypothetically, this could happen, da-da-da-da-da. I haven't calculated it yet, but maybe. Like, you guys are operating from so far behind. It's hard to do this every week and then have these half-assed refutations come out. It's if you're gonna play basketball, put the ball in your hand and shoot it or whatever you do with a basketball.
The term is arrogant ignorance.
Debunk it by not looking at it. I don't have to look at your data to know how wrong you are. Let me just fire from the hip with some random bullshit that I think might affect it, and boom. I may ask it again if you heard it. Okay, nailed it.
We might be multiple minutes off on every measurement, but how dare you use a distance? Like, nah, dude, we're not doing that, bro. Like, eMBO, you're a pretty nice guy, and we've had some nice conversations, so I'm not gonna like disrespect you or anything. But the continue on of, you know, all distance is globe distance is, you know, that's not. Don't care. If all distances were globe distances, then your occlusion timings would match what's predicted.
You're saying multiple minutes there, but the astronomical refraction at 0 degrees, it's like 30 arc minutes. That's the refraction when at the moment when a celestial object is hitting the horizon. So if you just ignore refraction, then
when you say keep ignoring refraction, what do you think you mean by that? I can't pull over any further. K through Q here is all refraction analysis. E through H down here from E36 to H36 on down to H40 and E40 is all refraction, all compensated for the globe. So this whole like does like I can't, man. It means nothing. Were you not here at the beginning when I went over the refraction stuff? The Novaya Zemlya, how much refraction is needed? I'm willing to give you all the refraction, but you can't just be like, oh no, it happens to match the occlusion without breaking the law of reversibility. Like, I'm here for you guys, but what are you doing? What are you doing?
He knows that because he was like, hey Jesse, I checked their sheet, and when you said refraction isn't accounted, I see this column which is perfectly accounting for refraction, yet it's still not matching the flat Earth. What do I do, mate? And I don't know if he ever answered you on that, but maybe you should get back to us when you get Jesse's answer. You can relay it to us next week or whatever. So like you know that we account for refraction. It's all in there. For people just to say that
Yes.
stop.
Like Finky said, he has 10 cells labeled refraction. And not only are they labeled, you can click on the cells and you can see what they came from and how we're applying them, which is the pivotal part in understanding anything if you're going to critique anything about this. Because if I hear you're not accounting for refraction again as a hand wave dismissal, I'm going to have to just like not hear anything from you ever again.
Okay. Does this also account for the terrestrial refraction or only for the celestial refraction?
Sure does. We have a special terrestrial refraction down here too. Although we don't consider it because, like I said earlier, there's no actual intersection because the light rays don't converge at the refracted image, but they are here for funsies if you want to look at them. And then according to this, for Pike's Peak, there would still be an additional 4 seconds where the star is going to be above the peak. So even accounting for that refraction doesn't help, even if we gave it to you for funsies, which I agree I will, but no converging light rays means no actual occlusion. So even though I included it, it has no physical meaning here, but it is there.
Well, it does, because that's the location at which you're observing the mountain. The light from the mountain is bending towards the observer.
Yeah, so if I say the words, the light rays that are being refracted up to create the image that the observer is seeing that's raised up don't converge, so it can't cause an occlusion. Does that mean anything to you, or do you not? Is that a one ear out the other?
Wait, are you trying to say that a bending light cannot cause an occlusion? That it cannot hit something physical and be blocked because it's
After
bending?
the physical point of occlusion? No, it can't. After the light has already passed the opportunity to be occluded, who cares which way it bends after that? You're getting the same data. It's just you're just seeing it in a different location at the final point. Think it through,
Okay,
buddy.
so you have a bending light that's bending up to the point of occlusion, and then after it travels behind the mountain, it magically becomes straight because it passed the mountain. Is that what you're trying to say?
It doesn't matter what
No.
it does after the mountain. The point is that you see it or you don't, wherever you see it.
Yeah, and but your occlusion time is dependent on the place where you see the mountain, because that's the angle.
But not where you see it from. No, it isn't.
It's not dependent on the optical angle in which you see it. That's the whole point of this. That's why we go into stellarium and look at where the star is with respect to the peak, because that's the time that it actually was intersected and angularly aligned with something for it to be occluded. And from that, we can draw congruent triangles from the observer from the observer to the mountain peak, and from the mountain peak to the star, and have it all be congruent. The timing for congruence for the globe was back here. That ship has sailed. If there's a refracted occlusion going on, that's not even possible. It has to still intersect with the geometric intersection. So even giving that for astronomical refraction, they're up by 1 arc minute, which translates to 7 seconds. If you raise the altitude of the mountain peak by terrestrial refraction, they're still over the mountain peak by almost a full arc minute. They come out to 48 arc seconds, which translates to 7 real seconds. So they're still above the peak geometrically, even on the refracted non-convergent light ray image that doesn't include anything. So it still doesn't help. And I don't like going in circles. So I would appreciate it if you actually took time to look at this instead of repeating, you don't account for refraction, so I don't have to listen anymore. Because now you've been made fully aware that that refraction is being accounted for. And I would much appreciate your opinion on how we're handling the accounting for refraction. Perhaps we're doing it wrong. But to say that we're not accounting for it at this point would just be a lie. And you're not a liar, right?
Okay, so let's just not continue this. You said that you converted the angle to seconds. And how do you do this? Do you just plug it into 15 degrees per hour?
No, there's actually, you would think that, but in latitude dependent, there is, and also kind of angle in which you're looking at dependent, the stars drop at a different rate. So we have the rate calculated for each peak, for every for the latitude that it's at. We took a couple seconds of its descent in stellarium, plotted that out for its actual, what it comes out to be angle for time wise. And then we also went into stellarium, double checked where the stars we're at to make sure our occlusion stuff, or to make sure our timing differences were accurate. So we have a drop rate offset here for 15 degrees per hour. Instead of 15 degrees per hour, you'll see it's 9.97 or 10.97 degrees per hour, 11.58 degrees per hour, etc. So all of these come out of that. And then you can verify the angles in Stellarium, like I said, to make double extra sure that we're good to go. Because the thing about our spreadsheet is that we super like verifying with globe tools to make sure that everything is steel manning the globe as strongly as possible.
Okay, nice. Yeah.
So to answer your question, there's a formula for it, and I can give it to you, but you can also just verify it by dropping the star in Stellarium for the observer, and then doing it yourself that way.
No, I know that it works different way because the celestial sphere, it tilts based on latitude. I was just trying to figure out if you know about this. And also it varies because of refraction.
Yeah, not only do we know about it, it's built into the spreadsheet. All of these tabs over here that are abbreviated peak names, those are where you can find the vertical descent differences.
And
Thank you for bringing that up, though. Much appreciated.
Nice. And do you also and in that equation, do you also account for the fact that the lower the star is above the horizon, the slower it's going to move?
Yes, as you can see here, where's my data table? So you see here, it starts off at like 10.97, 11.58, and then down here for North Peak, where the star is said to be below the horizon, its rate of descent has dropped to 4.14 degrees per hour. So yes, the answer to your question is yes. And we double checked it with Stellarium to make sure that we were doing it right. And by we, I mean Brian. Shout out to Brian. He did all of that. And then I just implemented it through the function that he gave me. But yes, we are aware and we have compensated accordingly. All right, lads and ladettes, I think we will wrap up for the evening if there's nothing further. All right, lads, tune in tomorrow for Ether Cosmology or Ether Roundtable 110. We will probably be doing a reading night of some sorts. And then Friday we'll be on Twitter for the Friday community Twitter space. And then Sunday for Globebusters, Stone is going to be doing a breakdown of an old Eric Dubé video where he talks about using a spirit level on a plane versus using a gyroscope on a plane, and then Stone actually got a pilot to get some measurements with a gyroscope in a plane. So we'll take a look at that, and then for the conclusion, Stone will be going over how plan landing radar systems are used to guide planes in for their landing, and how the angle of descent doesn't account for any drop over distance for like a difference in elevation when they're coming in for their landing. And all of this can be verified by their extremely precise landing radar system that they have. So he's going to get into a one-stop shop breakdown for the whole saga there, and we'll get to find out what happened with the whole Shiva thing. If anyone was following that on Twitter, you'll get some answers on how all that went down, and the proposed experiment that Stone had put up.
Just to be clear, no gyroscopes were used in this process, and it's also referred to as the ILS glide scope experiment. Glide slope, let me get that right. People hate when I use glide scope. Yes, the ILS glide slope experiment. See you guys on Sunday.
Nice. Oh, sorry about the gyro. I could have sworn I remembered you had a pilot could take a little gyro in there or something.
Oh, yes. Entirely different experiment. Yes, indeed.
Oh, gotcha. Okay, I mixed them up. Okay, cool. All right. So yeah, we'll stay tuned for that on Sunday to get the full history on that. And then we'll be back again on Monday to go over whatever was presented following this presentation to see if there's any actual meaningful globe refutations and see if we can find that variant radius that's been whispered and rumored about. I think I thought I saw it. It wasn't there though. I thought it was at line A58, but there's nothing there. It's blank. There was nothing there. Turns out the only radius is B20. So anyway, all right, lads. Geo, thank you as always. Very gracious host.
Game, guys. Great game.
No doubt. Good stuff. Good stuff. About to get it popping here right now.
Ready, Jeremy?
Yeah. About to get it popping. Does anyone got a topic? Do anyone have any recap on what just happened or? What you got, Gally? Yo, mic check.
Loud and clear.
Yeah. Jake, let me ask you this. Jake. Can you have parallel lines in spherical geometry? Oh, he might be AFK.